Hello everyone, I'm Yaxin Ren from WMG, the University of Warwick. Today I will talk about the anode potential estimation and fast charge strategy of lithium cells. In recent years, the electric vehicle has fast developed, but the charging of the battery normally takes several hours. The charging speed is limited by the material of the lithium battery, as a fast charge could accelerate the set reaction of the lithium platinum. From research literatures, the set reaction normally happens when the lithium battery anode potential is low. However, the anode potential is difficult to be measured directly in the commercial cells. So in order to prevent the lithium platinum, it is important to estimate and monitor the anode potential in the control system in real time. The observer will be designed based on the electrochemical model of lithium battery. The basic model is a P2D model, which describes the moving behavior of lithium in electrodes and separator. But this model is too complex to be used in a controller. One simplification of the P2D model is a single particle model with the electrolyte, the SPME model. The model uses the partial differential equations to describe the concentration of the electrodes and the separator. In order to transfer the partial differential equation into ordinary differential equations, it will need hundreds of orders, which is called the full-order model. The full-order model is also complex to be used in real-time controller, so we need to reduce the order using the mathematical method to simplify the model. And then linearize the nonlinear dynamics to finally transfer the model into a linear model with less complexity. The comparison among different models is shown in the table. For example, when the lithium cell is discharging with a current of 2 cells, it will take about half an hour in experiment, while in the simulation, the full-order model will take more than 300 seconds. The reduced-order model takes 6.8 seconds, and the linear model takes only 4.5 seconds, and all models achieving a similar performance in tracking the value of the experiment. And the longer time in real-world experiment, the more benefit the linear model can get with less simulation time. Therefore, in real-time controllers, such as the battery management system, more sampling points can be included in every time unit. After that, the linear model is used to design the observer to estimate the anode potential, and use the estimated value in the control loop for fast charge strategy. The observer uses charging current as the input and the terminal voltage as a feedback. The error between the estimated terminal voltage and the real voltage measured from the cell is used to drive the observer to track the state value of the real cells. Then, even though the anode potential cannot be measured directly, it can be estimated from the observer. The observer performance is validated in the traditional constant current, constant voltage charging strategy, or called CCCV. In this strategy, the cell is first charging with a constant current until the terminal voltage reaches the limit. For example, the 4.2 volt in the case. Then, to avoid the overvoltage of the cell, the charging current is reduced to maintain its terminal voltage at a constant 4.2 volt, until the charging current is less than a threshold to stop the charging process. So the higher charging current, the shorter charging time can be reached. In this figure, the solid line indicates the real profile of the real cell in experiment, and the dashed line indicates the estimated value from the observer. The charging current is the input to the observer. The terminal voltage is a feedback into the observer, which is used as a reference. Then, the cathode potential and the anode potential can be estimated from the observer. The estimated value is compared with the real value of the cells in experimental tests. The real value of the cathode and anode potential can be measured in lab because we use an approach called the 3-electrode cell that dismantle the commercial cell and assemble it into the PAT cell for the measuring the negative and positive electrodes, but it cannot be used to measure the commercial cell out of the lab. The result shows that the estimated cathode and anode potential tracks the real value in cells. Therefore, it validates that the observer is able to be used in charging controller to estimate the unmeasured values, such as anode potential. The charging controller is designed with a fast charging strategies. The traditional method is a CCCV, which I have introduced before. It is widely used, but have plenty of issues in fast charge. The most significant issue is lithium plenty and high cell temperature if applying high charging current. To reduce this issue, some research have proposed a multi-stage constant current, constant voltage strategy. It manages the charging current in different stages in order to reduce the cell temperature and the lithium plenty that occurs by the negative anode potential. Both the CCCV and the MCCCV use the terminal voltage as the only feedback into the controller. In our design, the anode potential is maintained by the controller using the estimated value from the observer. When the estimated anode potential reaches the preset limit, the controller will reduce the charging current. So the controller using both the terminal voltage and the estimated anode potential using the observer. Performance comparison among three charging strategies is given in the figure. The dotted blue line shows the profile of traditional CCCV. The red line shows the MCCCV approach, and the dashed green line shows the proposed CCAPES-CV, which maintains the anode potential using the estimated value. In addition, the cell temperature is also simulated in the result. Comparing with other two methods, the CCAPES-CV has avoided the negative anode potential and reduced the cell temperature during the charge. And also, it reduced the charge time, which only needs 80 minutes to fully charge the cell. To further compare the performance, the bar chart is used to compare the k-indexes of different fast charge strategies. The lowest anode potential indicates the probability of the lithium plenty. The lower anode potential, the higher risk of lithium plenty can happen. The result shows that the lowest anode potential of CCCV is about minus 17 mV, while that of the MCCCV is about minus 13 mV, and the CCAPES-CV has never reached the negative anode potential. Comparing the peak cell temperature, the CCCV reached about 41 degrees, while the MCCV reached about 38 degrees, and the CCAPES-CV only 36 degrees. Lower peak temperature causes less thermal issue of the cells and reduces the risk of destroy. As the strategy is for the fast charge, the charging time is also an important index to be compared. The CCCV requires about 97 minutes to charge a cell into 100% SOC, while the MCCCV requires 105 minutes to fully charge the cell, and the CCAPES-CV requires only 80 minutes to fully charge the cell. So the MCCCV is actually a trade-off between the protection of lithium plenty and the charging time. But the CCAPES-CV can reduce the risk of lithium plenty and high cell temperature without losing the charging speed. It can reduce approximately 20% charging time. So it obtains the best performance in all the three methods. So in conclusion, this presentation talks about the importance of monitoring the anode potential during lithium battery charging. Due to the anode potential is difficult to be measured directly, a suitable electrochemical model will be used to estimate the anode potential, and it needs to be easy enough to be applied in a real-time controller. In the fast charge strategy, it uses estimated battery states from the design observer to avoid the negative anode potential and high temperature. And the proposed fast charge method can achieve a faster charging speed, a lower temperature, and avoid the negative anode potential to reduce the risk of lithium plenty to extend the battery life cycle. But due to the current result just from simulation, in future works, we will validate it in the real cells in the experiment to test its reliability. Thanks for listening.